We've got two more sections on circles for you today in this video. The first one we're going to look at is on secants and tangents. So quick reminder on those definitions. A secant is a line that intersects a circle at exactly 2 points. So it's like a chord, but it extends beyond the circle because it's a line, not a segment. And then tangent is a line that intersects a circle at exactly 1 point, called the point of contact, or it can also be called the point of tangency. Okay, so tangent lines are perpendicular to the radius that is drawn from the center to the point of contact. And if we have a line that's perpendicular to the radius at the point of contact, then we can conclude it's tangent to the circle. So these two statements go hand in hand. If we know it's tangent, we know it's perpendicular. If we know it's perpendicular, then we know it is a tangent line. So let's use that to solve some problems. TP is tangent to circle O at T. The radius of circle, and that's a typo, that should be circle O, is 8 millimeters, and the tangent segment TP is 6 millimeters. Find the length of OP. So T, this is our point of contact or our point of tangency. And we know the radius OT is 8, and that the segment TP is 6. And this, excuse me, this diagram clearly is not drawn to scale. And because we're told that TP is tangent, we know that it's perpendicular to the radius. So this is a right triangle, and I'm looking for my hypotenuse, that side OP. And this is actually part of the 3, 4, 5 family, and you should know that this is 10, but if you forgot that, then you can always use Pythagorean theorem. So that is 10 millimeters. Okay. Another theorem is called the two-tangent theorem, and that is if two tangent segments are drawn to a circle from an external point, meaning the same external point, then those segments are congruent. So here on practice problem number 2, and I'm going to zoom in so you can see a little bit clearer. AB and AC are tangent to circle O, and they are drawn from the same external external point A. So that means that AB is congruent to AC from our two-tangent theorem. So we're given expressions for the length of AB and AC, and then we're told that OC is 5x, and we want to find OC, which is the radius of circle O. So how can we find what x is? Well, we can set those expressions for AB and AC equal to each other and solve for x. So this is just basic algebra. Move all the x's to one side, move all the constants to one side, and so 10x is equal to 5, which means that x is 1/2. So if x is 1/2, OC is equal to 5 times 1/2, which is going to be 5 over 2, or that would be 2.5. All right, so tangent circles. Tangent circles are two circles that intersect at one point. This could be externally or internally tangent. And then common tangents are when we have a line tangent to two circles, but it's not necessarily at the same point. So we have internal tangents and external tangents as well, just like when we have tangent circles. So looking at number 3, we've got a circle with a radius of 8 that is externally tangent to a circle with a radius of 18. So what that means is that they touch here. So these triangles are externally tangent along their edge at that one point. And then we want to find the length of a common external tangent. And so that external tangent has been drawn here, that AB, that's that common external tangent. And so we are going to have steps for finding that side AB, which is noted as x. So the first step is going to be to draw a segment joining the centers. So I'm going to draw a segment that joins the centers of my two circles, Q and P. Now, because I know from Q to that tangent point is equivalent to the radius of circle Q, which is 18, this is 18, and I know that the segment from P to the tangent point is the same thing as the radius of circle P, which is 8. So those are both 18 and 8. Okay. So we've drawn our segment joining the centers, and we know that that total distance would be 18 plus 8, which is 26. So that was step 1. Now step 2 we are going to be drawing a parallel line, or a line that is parallel to the external common tangent. And it's going to be going through the center of the smaller circle. So here's the center of my smaller circle P, and I'm going to draw a line that's parallel to AB. Now remember, because AB is tangent, that means that it is perpendicular to those radii, and if I'm drawing a parallel line, then that line is also perpendicular. So what we have here is a rectangle and a right triangle. So now remember, rectangles, opposite sides are congruent, which means if this is 8, then this piece is 8, and the remaining section would be 10, because if the total length is 18, I just took a piece that is 8, and I'm going to rewrite that because it looks a little tiny. Then the remaining piece is 10. So what I'm looking at now is this right triangle that we have made, and I'm going to redraw it down here. So in my right triangle, I know this side is 10, and I know my hypotenuse is 26. And what I'm looking for is that second side, which again is part of that rectangle, which means it's opposite AB and would therefore be the same length. So the last thing we're going to do is use Pythagorean theorem, or you can use your triple, to find the missing side. Now, this is actually part of a 5, 12, 13 family, so I don't need Pythagorean theorem. That missing side is 24. So x is going to be equal to 24 centimeters. All right, on to number 4. Circle P is tangent to each side of this quadrilateral ABCD. We're told that AB is 20, BC is 11, DC is 14, and AQ is x. We want to find AD. So this is called a walk-around problem. So I'm going to start by labeling all of these dimensions I was given. So AQ is x, AB is 20, BC is 11, and DC is 14. And what we're looking for is this length AD. Now, remember, tangents that are drawn from the same external point are congruent. So these two segments are congruent, these two segments are congruent, these two are congruent, and these two are congruent. So if AQ is x, then A to this point is also x. And that drew in kind of funny. This is also x. And if this whole segment AB is 20, that remaining piece would be 20 minus x. And because this segment's congruent to this segment, this one is also 20 minus x. And now we're looking at the same thing as we did with AB. This whole segment equals 11, so that remaining piece would be 11 minus 20 minus x. And that's going to be the same for both of these congruent segments, which leaves our remaining two segments that are going to be 14 minus this whole expression. So that's going to be 14 minus 11 minus 20 minus x. That's the length of both of these pieces. So if I want to find AD, well, that's going to be AQ plus QD. So AD is going to be x plus this whole expression here. 14 minus 11 minus 20 minus x. And now we're going to use order of operations to simplify this expression. So that's going to be x plus 14. I'm going to go ahead and distribute that negative into here. So that's going to give us minus 11 plus 20 minus x. So that's x plus 14 minus 11 plus 20 minus x. So the x's are going to cancel, and I'm left with 14 minus 11 plus 20, which means that AD comes out to be 23. So that's a walk-around problem. All right. Number 5. This is really just a review of distance formula and perpendicular slopes. So again, if we want to find the radius of circle P and its tangent at Q, what that means is I'm looking for the distance from P to Q. So if this is my x1, y1, and x2, y2, I'm just going to be looking for the distance between them. So 4 minus negative 2 squared plus 9 minus 5 squared. We are going to end up with 36 plus 16, which is 52, and that does simplify out to 2 square root of 13. So that's our radius. Now, if I want to find the slope of the tangent line, remember tangent lines are perpendicular to the radius, so if I find the slope of the radius, PQ, which again, y2 minus y1 over x2 minus x1 for slope, that's going to give us 4 over 6, which simplifies to 2/3. And then perpendicular, remember that is the opposite reciprocal slope, so the perpendicular slope would be negative 3 over 2. Right. Almost done with 10-4. We have concentric circles with radii of 8 and 10 that have the same center P. If xy is tangent to the inner circle and is a chord of the outer circle, find xy. So this is kind of a review of the very first section we did together, where we're going to be drawing in those radii. So the smaller circle would have a radius of 8, and my larger circle would have a radius of 10. If this is tangent, I know this forms a right triangle, so this is part of the 3, 4, 5 family. Each side's been multiplied by 2. So xz is 6 and yz is 6, meaning that xy would be the sum of those two and a grand total of 12. All right, last one for 10-4. Find the perimeter of a right triangle of the right triangle WXY if the radius of the circle is 4 and WY is 20. So this is going to be another walk around problem. This whole piece is 20, and I know that my radius of my triangle is 4. Or sorry, my radius of my circle is 4. So what I'm going to do is I'm going to let this forms a right triangle, so I know that each of these is 4. And I'm going to call this remaining piece on the triangle X. And then again, remember, the tangents that are drawn from the same external point are congruent. So this is also X, and the remaining piece of WY would be 20 minus X. And that leaves this piece also being 20 minus X. So the perimeter of this triangle is going to be all of those pieces added up together. And so these x's are going to cancel, and these x's are going to cancel, and I'm going to be left with 20 plus 4 plus 4 plus 20, which means the perimeter is going to add up to a grand total of 48. All right, now quickly moving on to 10.5. This is just quickly how arcs are related to circles. And so you can read through these long theorems if you want, but this is the main summary. If the vertex of the angle is at the center, it's equal to whatever arc it encompasses. If the vertex is inside the circle, it's half the sum of the two arcs that it intersects. If the vertex is on the circle, it's half the length of the arc it intersects. And if the vertex is outside the circle, it's half the difference of the two arcs. So what we're going to do here first is identify each type of angle that we are shown, and then we can solve for the measure of that angle. So starting with number 1, we're told that FE is tangent at E and that the measure of arc DE is 80. And then we want to find angle DEF. So where is the vertex of angle DEF? Well, it is on the circle. And so if we look back at our summary, when it's on the circle, it's half the arc. And if our arc, we were told DE is 80, then that means it's going to be half of 80, which is 40 degrees. Okay. Number 2, find the measure of angle A. Well, where is the vertex of angle A? It is outside the circle, which if we look back at our summary above, if it's outside the circle, it is going to be half the difference of the two arcs. And so we're told here we've got the two arcs. One is DC, it's 100. The other one is EB, that is 20. So it's half the difference. So half of 100 minus 20, which gives us half of 80. And so this one is also 40 degrees.